Thank you. My name is Sanjay Bhatnagar. I'm a scientist. I work at the National Radio Astronomy Observatory. I have a background in physics and astronomy, but then veered into algorithm development because that requires a lot of physics as well. How to deploy the telescope physics in an algorithm that can be done efficiently, that's what excites me. So that's what I do. So all kind of, and I write now software, scientific software. So go ahead, judge me if you want to, but don't tell me what you conclude from that judgment. I don't want to know that. Or maybe I know that, what you'll say. So what is NRAO? It's an NSF-funded national observatory. The mandate is to build large radio telescope for the community, researchers in US and everywhere else. One of the two large observatories that we run is the very large array in New Mexico, which is where I work. And then there is this ALMA facility, which is in Chile, which is also run by NRAO in collaboration with the EU and Japan. It's a big component in EHT. It makes EHT actually possible. We also write the software that processes all that and is used worldwide. In this talk, I'll give you an overview of the RA, radio astronomy processing. What do we do? How do we do? Why do we do? And all that. And also about the work that we did with CHTC and PATH. I have a large number of slides here. I'll try to go over them quickly because I'm trying to address computer scientists, HTC community here, and a pool, the student pool that is actually even more important than OS pool, who have come for this talk. Thank you very much, and I'll try to address them as well. So I might have to go a little fast on some of them. The technical talk about what we did on PATH will be on Thursday by Philippe Madsen at 11 o'clock, at 11:15. So listen to that one for real technical details. So this is the telescope. The way I think of since morning is that it's the most interesting combination you can think of. Our data collection is distributed across tens of kilometers on the ground. So we have data collection which is distributed, which now requires distributed high throughput computing processing. So surely everything that can go wrong will go wrong in this combination, but it's been hard to think about everything that can go wrong. And almost everything did go wrong in the run we did. The reason why we did, and I'll show you why we do it this way, is basically resolution. Getting the resolution requires a large lens, and to produce a large lens in radio at radio wavelengths is hard, and that is solved by making these kind of interferometric arrays. So this is one of them. What we are trying to replace this one by is what we call the next generation VLA, NG-VLA. This one has 27 antennas. The next one will have 300 antennas. The current one is located in just New Mexico. This will be spread in US Southwest and into Mexico as well. So very large scale, thousands of kilometers. And this is a simulation of what we think it will look like. It's not there on the ground yet. But these are the two telescopes that are in US. There are hundreds of such telescopes around the world operated by various countries. SKA is one of them. But there are other telescopes in US, in Australia, in India, in South Africa. All of them have the same problem, which I describe as a large amount of data they collect, and they require very high throughput computing, very large amount of computing applied to large amount of data to process to make the image. That is the problem. Why do we do it this way? As I said, because of resolution. That if you take the largest single dish steerable telescope that's in Green Bank in West Virginia, it's 100 meters. Going beyond that in terms of single aperture is very hard. It gets expensive, clunky, and all that. And if you take an image of this is supernova remnant that I studied a long time ago. If you make an image with the Green Bank telescope, this is how you'll see it. And the resolution of this telescope is defined by the dish diameter here. If you do it with VLA, that's what you see, about 350 times more resolution. And the resolution of these telescopes is defined by the maximum separation between the antennas. So that's why NG-VLA is going to thousands of kilometers. The sensitivity of this telescope is defined by the total collecting area. So more number of antennas separated by larger distances is what we want. Both of these parameters increase the data volume that we need to process. How do we do that? The way we do is this array, two pairs of antennas give you one measurement on the Fourier plane. These are indirect imaging devices. We don't get an image directly. But one pair of antenna gives you one measurement on the Fourier plane. You take another pair, you get another pair. you get another pair of antennas, you get more data points on that. Now, if you can devise a backend processing hardware that can take all pairs with one antenna, you get that pattern on the Fourier plane. If you can take all pairs given from given array, you get that pattern. Fourier transform of this pattern defines, roughly speaking, is what we call the image. But you can see, I mean, so think of this red thing as a lens. It's a very funny looking lens, first of all, with a lot of missing data. Missing data is a problem, so we try to fill it. But we have a limited number of antennas, so we let the Earth rotate, and we call it Earth rotation synthesis. So as Earth rotates, this pattern rotates, and the Fourier plane keeps getting filled. But look at the number of points. Now, the number of points by the end of the day we have collected is of the 10 to the 13, 10 to the 15 data points, complex numbers. And that is what we need to process. So that's where the data volume comes from. But even if this pattern you take and take a Fourier transform, if the source in the sky looks like that, if you just take the Fourier transform of that, that's how the image will come out to be. It's the capability of the telescopes is 1 million to 1 dynamic range imaging telescopes. This gives you thousands. So there's several, 3 or 4 orders of magnitude in image processing quality that we need to get to. And that's what leads us to this problem. High performance computing using big data. That is the problem that these telescopes need to solve. So getting down into so this is posing the problem. How do we do it? The algorithms that we trigger are iterative. That means they use the same data a number of times. And that is fundamental. I don't think we can get out of it. And that is roughly the graph. The data comes in, that's on an irregular grid. The data lands on the Fourier plane wherever it lands. It's not on a grid. But to apply a fast Fourier transform algorithm to it, we have to resample it on a grid. So we sample, do a Fourier transform of it, you get an image like that. We do some iterations here to get to that image. But in that, iterations are not enough. So you Fourier inverse, reproject data onto this plane, compute the residual, and do this cycle. Typically, we do this cycle about 10 times. So the whole data that is coming in, terabytes of data, is read over 100 times. So that is just the imaging. And on Thursday, the talk that Felipe Madison will give will show how this was deployed, just this was deployed. But that's not all we need to do. We need to so these are the two big computing boxes, and that's the scaling. Number of visibility points, that's the total number of data, times about 10 to the 10, 10 to the 4, 10 to the 3, 10 to the 4 kind of flops to convert it into an image. And then a couple of iterations to just improve the image that you got. So that number of iterations is a multiplier to that. And then we have to reprocess because sometimes the parameters of the algorithms are not right. The image that came out is not right. So you need to reprocess the number of reprocessing. We also do a calibration. So sometimes calibration has to be redone. And then there is always presence of radio interference, which we need to remove. So these are the loops that we can go into. But what I'll describe today and what we did with OSPool was only this part. But I'm putting it here that long-term problem that we like to solve at NRAO, at other similar observatories is actually this kind of processing. Currently, if you look at this piece of the graph, which basically is making the image or predicting, given a model image, predicting the data, both of them are algorithmically similar complexity, and they drive the size of computing largely. And here is the proof of it. This is this box. The orange part is this box, whereas this box, which is another compute load, is that blue thing. So it's by and large, this is the highest nail that we need to solve. So let's address that problem. How do we solve? Or I'll explain to you what that problem is. That data lands where it lands. So think of this as these green points. And to convert that into a regular grid, we multiply each of these data points by a complex kernel and resample it on a regular grid. So this multiplier with 10 to the 14 data points is the compute load, roughly speaking, for that part of the thing. FFT in the relative cost of FFT is actually very light, very, very small. So the size of computing, if you convert, especially for NGVLA, it comes to about petaflops, 50 petaflops, or tens of petaflops that we need to keep up with the data rates that it is going to output. What we need is large-scale parallelization, very clearly. I mean, that kind of computing is not going to come from a single computer. So we need to do some work on our side in terms of making sure that our algorithms are scalable on such large scale. Often when I talk to the HPC community, especially with the DOE people, their view has been, and we're trying to modify that, that their HPC problem is simulations. Somebody comes, does a simulation for 2 months, and they go away and they've got the product. That's not our case. We are pumping terabytes of data with petaflops of computing, and we'll keep doing it 24/7. That's exactly our problem. So computing needs to be efficient. It needs to be 24/7. And it needs to be seamlessly deployed on a heterogeneous cluster. No cluster of this size, I can imagine, will be a homogeneous thing. And this we saw with the spool. So that's another very strong requirement. This is mostly a software development thing, but it's still a killer if you don't do that. So what do? We clearly understand that we now need to collaborate with HTC, HPC communities, and even industry partners. So we have transformed the way we talk of algorithm was very, very jargony in terms of you have to be radio astronomer to understand what we are talking. So we transformed that into standard terminology, derivative, Hessian, update, directions, and all that. I won't go through the math, but that's basically our imaging problem, that this is the derivative of the chi-square with respect to the parameters of the image. That you can see that this comes out to be just making the raw image is computing the derivative, and then you put through an iterative algorithm to improve the process. This was converted into a graph, which basically is mimicking this thing in terms of an executable graph. And this box corresponds to this part, which is just making the image. This box corresponds to that part. And in the software, these were deployed as separate processes. Now, Myron and others came to our observatory many years ago, and at that time, we were trying to do this with CPUs. And we deployed this graph, which is this part, on 200 of them. So 200 data comes, it gets distributed into 200 of such processes. Each one of them makes a sub-image, which is then gathered and then piped into this kind of processing so that those iterations go on. You keep doing that iteration and again. This is the scaling curve. So the black line is the linear scaling. The line close to it what the scaling we got. And clearly, by the time we got to about 100, we expanded it to 200, but few hundred processes and starts tapering off. So this clearly is not going to scale it to that level. If you convert the CPU processing power for NGVLA, we require 1 million CPUs running. That is not going to scale. So we invested time in trying to put that onto a GPU, and we got that kind of a scaling on a GPU. So 200 of those processes now get replaced by one single GPU running. We got about 200 times speed up, but that still leaves you still require thousands of GPUs running. Smaller problem, looks like doable, but still not an easy problem. That's what you get. So that orange thing got down to comparable to the other blue thing. But still, when you scale it to NGVLA, the orange thing will still be the biggest problem. In real life, what happens, you can talk of these numbers, but as an astronomer, as a PI, when I wanted to make the image of this supernova remnant, this again took 2 months on a single CPU or a couple of CPUs. But if you go to GPU, from 7 to 10 days, it gets down to 2.4 hours, 2.5 hours. So it's actually a very tangible, very useful thing as a PI, that you are actually able to make an image. If you make a mistake, you can do it again a couple of times. That is where I think we need to be with NGVLA. This is a smaller problem with the current VLA. With 50 petaflops computing, you should be able to do that. You should be able to make a couple of mistakes and still get there. So this scaling with GPUs is what we are trying to work on. Thousands of GPUs running and making the image. And that's where we got to talk to people in CHTC and NRP and UCSD and everything. Did an experiment with a data set that has been lying in our archive for 10 years. It was taken 10 years ago, could not be processed. Actually, we tried to do it on SDSC about 7 years ago. One cycle, we need 10 cycles. One cycle took 14 days. They politely asked us to get out. We wanted to get out. We were all fed up with that. We have 14 days to make one image is not feasible. This reduced that kind of a terabyte, that kind of a throughput, 1 terabyte per hour on the OS pool. The whole thing, which did 10 iterations, finished in a day. We made a couple of mistakes, we made it again, and we finally got the image. This is not displaying it well here, but believe me, this is the deepest image that the radio community at any band has been able to make. Uh, I can't show you here, but there are all these blank things have a small dot. That's a distant galaxy. Again, cosmologists and other people who look at the evolution of the universe and those kind of things, H1, how does that evolve with redshift or with time? Valuable data here, absolutely valuable. This current telescope is capable of doing, but we don't have the processing capability, or we maybe have now. NGVLA, this took 10 hours of data to get. The NGVLA will give you this in about 45. 1 hour will get you that limit. So people are going to push this even farther away and requires more computing. So that is the kind of throughput we could get with the current experiment. Now, quickly, I mean, this is the software that we use. If anybody wants to talk to me later, we are trying to convert our existing software into a library of algorithms so that they can be easily deployed on different kind of things, rather than take 40 or 20 FTE group to modify the software. Also trying to deploy exact same thing that we did with Path directly on NRP. That experiment is actually going on as we speak. We're pretty happy with what we have been able to do, but I think scaling has to be done now. So what are the current and future needs? KSG is the key science goals of the VLA. That will generate about 50 terabytes of data per hour. We produce this in several days right now. That will produce in an hour. And the throughput that we get is out of that, 50 terabytes. What we have been able to achieve is about 2 terabytes per hour right now with the current experiment. Need to scale it to about 50. Computing, infrastructure development, interleaved processing of multiple projects. This is a graph of various nodes running in the experiments that we did. Yellow is the data in. This is the data out. Red is actually the compute. It's a small part of the entire time that a node was blocked. So that's what I meant here by interleaving processes, so that when one process is pumping in data or pumping out the data, some other process should be using the GPU. Interfacing with the telescope storage archive, that's what I meant by. So we have an archive, whether it's staging there, I don't know what terminology to use, or it's an archive, I don't know. But one way I see this scaling to other radio astronomers using this is by they being able to go to our archive and say that, okay, I want this project to be deployed on whatever framework is there and get me the image. The other thing is, in this experiment when we did, and Brian will know, there were a lot of humans in the loop. There were a lot of people working overnight, making sure that nothing crashes. Things did crash, they fixed things in real time and all that. That many people in the loop cannot scale. So that is the other problem the one has to fix. And the other problem which I have not written here is, in my mind, is cultural. That radio astronomers have to get used to this kind of processing, but they will never get used to this kind of processing if there are hundreds of people required to run one imaging. So those are couple things. Edge caching, by that I mean that I'm told that when we send a piece of data, a bucket of data, and it processes on a remote node, it gets cached there. That is edge caching. But the same piece of data we use again and again. I'm not very clear whether that edge caching is helping us, because next time that data is going to some other node and that is not cached, so we are transferring it again. But if, as Myron was suggesting this morning, if we can have a mechanism where if we transfer a data to a remote node and tell it that we are going to use you 10 more times, stay there, that would be very, very useful, I think. Parallel processing at large scale, of course, is necessary. So the reason why I'm here, and this is my first time, so thank you for having me here. It's already a very useful meeting, is I think we need to collaborate in the sense that I think of that we have the data, we have the problem, you have the resources, you have the framework. We need to collaborate, figure out how to make them usable reasonably well. What somebody described during that run, that this was a hero run, it was a hero run, a lot of people involved, that has to go away. And on our side, we need to develop new algorithms, particularly cache-friendly algorithms or algorithms that reduce the amount of time it takes. Uh, this is just the conclusion, but I'll leave with this slide. That is a number of people I'd like to thank. The Bryans from CHTC, Maron, Christina, Greg, Frank and Cynthia from US SDSC, people from NRP, Cocos, the GPU deployment is done by Cocos, and we talk to the Cocos gang quite a lot, very, very useful to talk to them. We regularly talk to NVIDIA people who give us a lot of very useful information. This is the NRAO team, which is sort of international team of radio astronomers who build the software, and my group, which is the algorithm R&D group. So thank you, everybody. Now I'll take questions.